DisplayPort DP has played an important role in many electronics products, ranging from mobile device, cell phone, to automobile application. Therefore, in this video, I'd like to provide an introduction to DP from a high-level point of view, including the design requirements and challenges. The original common video standards for computers were Digital Visual Interface (DVI) and High Definition Multimedia Interface (HDMI), but both standards apply high voltage drivers and receivers under DC coupled serial link in the interface. What could be the issue of the high voltage for higher PPA requirement? Correct. To achieve high performance, low power, and low area, we may need the most advanced technology, but it decreases the supply voltage as the process geometry shrinks. Therefore, the DP provides a lower voltage AC coupled video link to integrate a high-speed video interface into the GPU over generations. Again, the lower voltage AC coupled link not only allowed continuous support for a single serial standard as technology advanced, but also enables new applications of high-performance video links. What's the obvious difference between HDMI and DP? Bingo! Speed or bandwidth. As you can see from the bandwidth chart, the DP beats the HDMI's bandwidth for over 60% capacity to support a higher refresh rate and a high-resolution display. After understanding why we need a DP in addition to other old standards, let's understand the DP's unique interface. A DP link comprises a unidirectional main link from a source device to a sink device, a bidirectional or serial channel link between the source and sink devices, and a unidirectional hot plug detect link from the sink to the source device. For example, the source device could be a video or a graphic process unit GPU, and the sink device could be a controller of a display. If you are familiar with most serial link standards, you might notice the DP links are too complex compared to other single main link. Let's look at a few images and figure out why we need additional links in DP. The first additional link is the serial channel, which is used for the link management. Therefore, the default mode for the link measurement is only 1 megabit per second transfer rate bidirectionally of the matrix encoded. To make the link measurement support compatible with the old video link, the aux line drivers are in a high voltage domain with no power or speed constraint compared to the main link's low voltage domain. In addition, the aux could also support other fast mode if needed, even though the usage is rare. Therefore, that could be a good motivation for separating the 1 megabit per second aux from the up to 20 gigabit per second main link. The second extra link is the hot plug detect (HPD), which is a critical feature of most links and a must-have in most devices. For example, if you must turn off any device, such as a cell phone, every time you connect or pull out a cable connection, that will be annoying. That's the reason most devices must support hard plugging, such that you can remove or insert any cable into your phone without turning off and on the devices. Then, the sink device to provide an HPD signal to the source device is a must, such that the source device is aware of the sink device present, absent, or interrupt request. After understanding those extra links, let's look at the main links feature and the corresponding design requirements in SerDes. First of all, for the unidirectional link, we call the transmitter a source device and call the receiver a sink device. Second, since the video audio information has lots of tolerance, the link bit array less than 1E-9 is good enough. Third, the unidirectional main link should support 1, 2, or 4 lane configuration along with the chosen line rate for different throughput or bandwidth needed. Lastly, both the line rate and number of link configuration should be communicated over the aux between the source and sink devices. For example, the maximum bandwidth could be 80 gigabit per second if we choose the line rate of UHBR20 and 4 lanes configurations. If we look at all supported data rate, you may wonder what the design difficulty would be. Think about the signal integrity images for 5 seconds. Correct. The input data of the DP sync device will be very jittery, and the eye is closed because of the eye width margin being 0. What should we do? Right, having a CDR of a wide tracking bandwidth that could open the eye width and the eye opening by improving its JTAL. Similarly, at such high speed up to 20 gigabit per second and 1 meter or 2 meter cable, that will cause the bandwidth limited input data with ISI at the receiver input to cross the input eye because the eye high margin is being 0. Then we definitely need the equation to open the eye opening for sure. Therefore, the DP specifies the reference EQ like CTOE for HBR and HBR2, such low data rate and low loss, by adding the DFE for HBR3 or any UHBR up to 20 gigabit per second. Therefore, any device must outperform the reference EQ to pass the JTAL compliance test easily. For the DP source device, not only the output swing level should be adjusted, but also the equation level of the FFE can be programmable. What would be the use case here? Right, we have a trade-off between power consumption and signal integrity. For example, if the cable between the sink and source devices is short, the source output swing can be minimized to save power consumption. On the other hand, if the cable connection between the sink and source device is very long, the churn loss will be a lot, and the source device output swing must be maximized to keep the link transmission robust. In addition, the source device FFE may boost to a maximum level to reduce some ISI going to the sink device. Here are a summarized image of why we need the DisplayPort DP and its development in SerDes. The DP provides a low-voltage AC coupled video link to integrate a high-speed video interface into GPU over generations. So, DP not only supports a single series standard as technology advances, but also enables new applications of a high-performance video links. Then, the DP seems to beat the HDMI and DVI to other video standards. DP links compromise a unidirectional main link from a source device to a sink device, a bidirectional auxiliary channel link between the source and sink devices, and a unidirectional hot plug detect link from the sink to the source device. Most and foremost, the unidirectional main link should support 1, 2, or 4 lanes configurations along with the chosen line rate for different bandwidth needs. Then, the aux should communicate both line rate and number of lane configurations between the source and sink device. The design challenge at the DP sync devices is to tolerate any jittery input and bandwidth limited input data with ISI. Therefore, we must design the CDR and EQ of the sync device well enough to achieve a wide tracking bandwidth and outperform the reference EQ to pass the J-Tau compliance test easily. For the DP source device, it's straightforward to have a trade-off between power consumption and signal integrity. For example, if the cable between the sync and source device is short, we can minimize the source output swing and save power consumption. If the cable connected between the sync and source device is very long, the channel loss will be a lot, and the source device output swing over FFE must maximize to maintain the target bit array robustly. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback. And please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.